Welcome everyone. This is the talk for Intro to SDRs, or Software Defined Radios, if you guys have not heard of them. We'll go over some pretty high level stuff that I think is important to talk about for intros to software defined radios, as well as some a little more like technical definitions and such as you're learning about radios that are, I think, pretty important to know just getting started. So, to talk about myself, I have been in a couple of local groups such as PHX2600 and a couple other local groups like DEFCON 480, DEFCON 602. I've been around for a couple of years. I was a college dropout. I am a pen tester for a company in the Midwest, and actually not a shark, nor am I obsessed with sharks. So there is that. Going on to the actual talk, though, about SDRs. What are they anyways? You don't need a ton of hardware for radios anymore. You used to have things like bypass filters, low pass, high pass filters, like all these different kinds of filters that were actual physical hardware blocks, amplifiers, anything that you needed for physical radios before. And most of that stuff you don't need anymore. With some of the new technology like field programmable gate arrays, general purpose processors, and digital signal processing, a lot of that is making radio a much cheaper solution, and it's much more accessible, especially on the consumer market. So it's quickly becoming the dominant form of radio communications. If you look at something like this Harris Falcon 152A on the left, which is, if you've been in the military, they're referred to as bricks. These have been software-defined radios that I think were distributed out since the 90s, and they are the de facto standard for infantry units, at least in the U.S. military. So, yeah, pretty interesting devices. But you can do a lot more than just communicating with them, such as things like tracking flight information through ADS-B. That's a pretty popular one. That's what I like to show people if they've never heard of radios. It's a great introduction. Listening to things like emergency services. In my area, we have Project 25-1 radios. So the whole region communicates using those, so anything that's not encrypted traffic you can easily listen to. A lot of interesting things. Sometimes those services are delayed because of public safety reasons, but that depends on your region. Listening to your favorite radio stations. If you have any, FM or AM radio stations that you like to listen to, but you only try and listen to them while you're in your car, your software-defined radio, you can just set it up and listen to it at any time of the day. You can get satellite imagery from satellites passing over. That's pretty cool. I haven't tried that yet, but I think there are some Russian satellites that I've seen some people getting imagery from for weather, and that's super cool. You can listen to ham or amateur radio stations. CB radio is another big one too. This project here, using it communicate with Wi-Fi, using the Blade RF makes it act very similar to what you would get from like Wi-Fi card. I don't know about any of the actual benchmarks on that. That's why I'm curious about that project, and I don't have the equipment for it yet, but I want to test that one out. It looks super cool. And there's other things that are more interesting, like Tempest SDR, which is a side channel attack that grabs emissions coming from monitors, radio frequencies that are being emitted from monitors, and you can pick that up and possibly see what's being distributed to the screen. So those are just a couple of examples of things that you can do with SDRs. Some of them may be restricted by the hardware, the SDRs that you're buying, but most of these are generally accessible from something as cheap as like the RTL SDRs. And so we'll go into what I recommend in a minute, but if you're in the US, a lot of these bands are going to be, I think these are all US allocated, so if you're in Europe or the Middle East or Asia or Southeast Asia, these may be different in terms of where these are allocated. So like ADSB is 1090, I think, across all of the US. I don't know if that's the same in other places, but ham bands generally in the US are 420 to 450 megahertz, with 2 meter ham bands being in like 144 to 148. So that'll definitely vary. I think the UK has like some different ones, like a couple megahertz lower. So just be careful and check your what's allocated in the country that you're in before you transmit on those. If you're looking for those services too, I would use that as a reference to listen to that stuff. So breaking down into modulation and demodulation, I think this is a pretty important thing to cover too. If you don't know what modulation and demodulation are, that is what the physical processor or is basically using to break down that information that's coming in from those radio waves or from those carrier waves, and it's using that during digital signal processing to figure out what information's coming in. So that is also where the term modem comes from. So if you have a modem and router, they are modulator demodulators. A little bit of interesting facts there. But going into this, so there are multiple ways of modulation. These are just a couple of common ones that you might see, such as amplitude modulation, which varies the amplitude or the power of the carrier wave. So in this GIF at the bottom right, you can see a better visualization of that, of how that's modulating, along with the frequency modulation, which is varying the frequency of a carrier wave. And that is what is being, that is what is determining what data is being sent. Going through frequency shift keying, what they'll do is for shift keying, there will be a number of specific frequencies, or things like specific phases that may denote a certain key or a certain value. And then when they're going through and using, let's say, frequency shift keying has two distinct frequencies, when it's transmitting frequency 1, let's say that that's a value of 0, and then you could have frequency 2 that's a little bit higher, and that's denoting a value of 1. You could do that to encode and create binary data for a computer to interpret. That's more common with like phase shift keying. But with frequency shift keying, you'll see this commonly, and I think the most common thing that you'll see these in is garage door openers. They use frequency shift keying a lot to transmit all that information to the receivers on the garage doors. So phase shift keying is a little bit more complex. There is this whole modulating frequency, and as long as it's continuing perfectly fine in this phase, that is denoted as a, let's say that this is a 0 the whole time. If you're trying to switch to send a 1, you'll see this the phases switch halfway through when you're talking about how the frequency is being transmitted. Sorry, I explained that one poorly. For me, I'm a visual person, so this one's a lot easier to explain visually. So, yeah. Sweet. So, going into the actual buying of radios. So, There's a couple radios that I would recommend, mainly, and I have the prices up here, not based off of what you can afford, but based off of what I would recommend. First off, which is I would recommend everybody go out and buy an RTL SDR if you're even interested in software-defined radios. These little guys I've seen them for usually less than $30. You could probably get them for about $20 to $25. I think some of their newer stuff that has slightly better hardware is like $35, but it's all around that price point of $30. They cannot transmit anything, so if you're looking to do something like communicating with Wi-Fi back and forth, or transmitting on ham radio station or ham radio frequencies, you can't do that. But you could listen to things like ADSB, etc. The bandwidth here, bandwidth is how much of the radio frequencies these radios are going to be able to catch all at one time as it's listening. So let's say that you're listening to like a trunked radio system that's from 800 megahertz. It has let's say it has 4 channels, and it's 800 megahertz to 816 megahertz, and it's split evenly. So it's like 800, 804, 808, 812. If all of those control channels are bigger than 2.4 megahertz, you would probably need multiple RTL SDRs to listen to those different control channels. So, but that wouldn't be a problem with, say, the Hack RF1, where it has that bandwidth of 20 megahertz. It could capture all those control channels and even possibly listen to the data channels that are being sent on trunked radio systems. So, bandwidth is something that I put in here as a consideration. The main thing is the frequency band. So for the RTL SDR, you can't go above 1766 megahertz. That is a hardware limitation on that part. Now, you can get around that with the RTL SDRs, and we'll go into that I think on the next slide. But for the most part, if you just get the RTL SDR, you're not going to get above 1766 megahertz. So you may be limited from listening to things like Bluetooth or Wi-Fi. With the Hack RF1, you're going to get a pretty wide range. I mean, you cover almost every single RF frequency except below 1 megahertz, which can be fixed again, but it has a bigger bandwidth, and it can transmit and it can receive, but it can't do it at the same time, so that's what we would call half duplex. The devices on the right-hand side that are full duplex can transmit and receive at the same time. So that is something that's worth noting. The Hack RF is a little more expensive. It's around $350. I have seen some on AliExpress for $180-ish, I think. People have asked me before if those are worth buying. To tell you completely, I don't know the answer. I don't know if they're actually good, but if anybody here has bought one, let me know. I want to do some testing between my Hack RF one and the AliExpress one, and if they're good, then I'm going to start recommending the AliExpress one. So, the other ones on the right-hand side, like the USRP B200 and the Blade RF, are definitely going to be in the more expensive ranges of $500 up to, I think that B200 Mini is $1,000 or $1,200. They're pretty expensive. If you're doing pen testing and you're using RF stuff, most of the time you're probably not even going to need full duplex stuff anyways. There's just not really a point. Even for Wi-Fi pen testing, you might as well just get a cheaper Wi-Fi card, or the Panda PAUs, anything like that. So no point in buying a Blade RF for that. But They have a way bigger bandwidth usually, and sometimes a little bit less of a frequency range, but they are way better devices hardware-wise. So if you're into radios and you've been around it for a couple years, and you're like, hey, I want to spend a ton of money, go into those. The Kraken SDR right below it, I threw that on here because I think it's kind of a cool little device. What it does is it takes 8 of these RTL SDRs and it ties them together into this crazy powerful triangulation station is the best way I'm going to explain it. They have more information on their site, but they're super cool. If any of you guys have ever done a fox hunt, it's basically using that is basically cheating on one of those. If not, we can go into that after the talk. So yeah, my recommendation there, just to make it short and simple, RTL SDR, and then if you're more interested and want to get into more things, go for the Hack RF, and then from there it's kind of do whatever. Going more into the accessories, so up converters and down converters are what's going to allow you to utilize, like the RTL SDRs are going to be able to listen to things like Wi-Fi frequencies. Not very well, because of bandwidth issues, but up converters and down converters will do things like converting low radio frequencies to higher intermediate frequencies for the SDR to interpret, or like the down converters, converting high radio frequencies to low intermediate frequencies. So the high radio frequency, or for a down converter, if you have a down converter with the RTL SDR, you could technically get into the 2.4 gigahertz range, and listen to those frequencies and try and do things with that. But outside of that, there's things like low pass filters. These are filters that allow any signals that are lower than a select frequency to pass through. With software defined radios, we don't really have to worry about these kinds of filters as much because a lot of filters are going to be software defined. That's the cool part. But you can buy hardware filters still, as they can be more effective in some cases. So another thing is the high pass filters are the opposite of low pass, and then band pass is for select frequencies. I haven't really seen a lot of band stop filters being bought, so if you need that specifically, then do that. But for the most part, all of this stuff can be thrown into software except for the up converters and down converters. Those are probably the more important frequencies to get into, or the more important accessories, sorry. Also, going into a tiny bit of antenna theory, there is a whole book that I would recommend if you're interested in building antennas, as antennas are a very big, important part of radio frequencies and radios in general. So just to start off really quickly, to calculate the wavelength formula, wavelength is velocity divided by the frequency. For all intents and purposes, velocity, radio waves travel at the speed of light at all times. So to simplify that, I usually use the wavelength in meters is 300 divided by the frequency in megahertz. That's going to be the easiest way, in my opinion, to figure out what the wavelength is. And that's very important because the efficiency of the antenna can depend on the length of the antenna compared to the wavelength. So things like quarter wavelength antennas are just the wavelength divided by 4, or 5/8 wavelength. I think that's pretty self-explanatory. Half wavelength antennas, of course, being the most common dipole antenna. You'll see these a lot with, I think, like Yagi antennas generally are dipoles on their sides, and they're just an array for direction. So The ground components, these are important, especially because a lot of SDR antennas that you're going to see will be like quarter wave or 5/8 wave antennas. It's important that you have a ground component, which is just literally any metallic surface or hard solid surface that's, I would say, probably about like 4 to 6 inches bigger than the base of the antenna, would probably be efficient. So for having a ground component, it is important because if you don't have one, your antenna is not going to be as effective. You're not going to have any resonant energy, or you're not going to capture as much data effectively as you can if you have that ground component to reflect that other quarter wavelength of the radio frequency. So I'm not going to bore you guys with that too much. There is a whole book that I would recommend, and I have the resources, and I'll post them at the end of this talk and on the YouTube video description when we upload this. So going into general software, these are a couple of my recommendations for software. Some of these are ones that I've touched. I think for general purpose software, I've taken a look at everything except for SDR Sharp on this page. So SDR Sharp I have no experience with, but GQRX, SDR++, and SDR Angel I have all used, and I prefer SDR Angel the most, but it also depends on the use case. So for general purpose, those are just a couple of recommendations. For trunked radio software, Unitrunker I haven't gotten set up, but I know a couple people who have that set up. And then SDR Trunk, I have set that one up and used it. I've heard a couple people having trouble with that one. Personally, I haven't run into too many issues with it, but I did get it to work. I can't demonstrate it right now, but maybe in like, I don't know, half an hour or so we can try and get it set up and see if we can listen to emergency radio services out here. Miscellaneous software that I threw in there, Tempest SDR, because I think that's a super cool side channel attack, and the Blade RF Wi-Fi stuff, that's super interesting, and if anybody has a Blade RF, let me know. I want to see this in action. So there's a ton of more software out there. RTLSDR.com has their whole list of RTL SDR supported software, so if you're going to discover more things, there's a shit ton more. So other references to for signal identification, these are really important because if you're going through and you find something interesting and you don't know what it is, SIG-ID Wiki can pretty much cover most things. Even I think they've had like some weird rare signals that are like, hey, I've never heard this, or there's a number station out there, what is this? And they go through and you can search by frequencies and figure out what you're looking at. Radio reference is also important. That is useful if you're listening to any kind of amateur stations, or at least in the US here, you can reference most any kind of licensed station by the FCC. They're all on radio reference, so that's pretty useful. For antenna theory, Tutorials Point has a pretty decent overview of like an intro to antenna theory kind of thing. You can click through it. I would say it's average, but if you really want to get into the woodwork and go really off the deep end, the antenna theory and analysis and design by, I think his name is Balanis. That book is insane. So go through. That's like the de facto standard for learning anything about antenna theory, and that's this Wiley link right here. If you're interested in just buying a whole bunch of stuff, New Elic has their up converters and down converters. I listed the Hack RF1 from Great Scott Gadgets. And then Mouser and mini circuits, you can buy things like filters and other radio components from them. So I would highly recommend taking a look if you're trying to look for things like that. For the RTL SDRs, anything SDR really, RTLSDR.com has you. They are basically like Hackaday, but for radios. They will post all kinds of cool projects that you can look through and other radio frequency stuff and SDR news. So listed that there. And then at the bottom, I threw an ADSB exchange. If you're interested in tracking flights, looking through that information, ADSB exchange is there. If you want to contribute to their project, I believe they also would like that too. So yeah, that generally covers the intro that I have. So if you guys have any questions, I would say now's the time to ask them. And you can use either your microphone or text chat, either one. Could I get the slides? Oh, sorry. Go ahead.
No, I was just gonna ask if using like the HackRF and when you're transmitting, like what's the farthest you can transmit, or have you tested that with your HackRF?
So it will depend on the frequency, the antennas, and a lot more of like environmental factors, including things like weather. I haven't tried to do anything really with HackRF in terms of like transmitting past line of sight stuff. Generally, most of the stuff is going to be a line of sight, but I don't go for distance. So I think there have been some people that are like, hey, I can transmit up to like 250 miles or like 300 miles from line of sight if I'm on top of a mountain and my buddy's not, or something like that. You know, like there's, or, you know, communicating with like weather balloons. That's a possibility. So I don't have any data on how far I've gotten it to transmit. But there may be some out there for you, and I could probably look and see if there's anybody that has that data.
Sweet.
Can you talk about how the hardware works in a bit? Yeah, in a minute. We'll cover that after the talk. That one's kind of complex, especially depending on the radios. But is there any pre-built antennas that you would recommend? Yeah, there's a couple depending on what you're looking for. That's going to be a question of like which bands are you going to be in, or communicating with, because I have like a whip antenna for 140 to like 148 megahertz for ham radio, and then ADSB. I have two specific like new ELIC antennas that I've been using that I really prefer. So it will depend, but I have a whole list of antennas that I've bought that I can throw in here at some point too. So there was a mention of YouTube in the future. Yeah, so to answer Red Potato and I don't have the name there, it's cut off on my thing, but yes, there is mention of YouTube. This talk will be uploaded to YouTube. I have had 2 other talks uploaded to YouTube, I believe, or at least one other one. So we do have that. I may refer to Void Walk to see what the deal is with that. But yes, it will be uploaded to YouTube. Do you have any recommendations for learning the software suites you recommended? There's not really too many high-level learning curves that I would say that you would need to know, but really, like, if you're getting started on some of that software, a lot of it like especially the general purpose stuff is going to be mainly plug and play. You could, if you're looking at like some of the advanced features of those, it's either reading the documentation that's put out by the software or watching like a 10-minute YouTube video on it. I think the hardest time that I've had issues with for learning how to get set up was setting up the SDR trunk stuff, but I was reading through the documentation for 3 or 4 hours, so that may be, yeah. Spore, I am recording from my desktop, so yeah. I presume that while ADS-B radio is sold to be used on 1090 megahertz, you can repurpose it for other frequencies. Yes, so you could technically repurpose any frequency for any use case, but it would really depend on, like, the FCC, at least in the US, has a lot of, pre-allocated things, so you can't like transmit AM like amplification modulated signals on FM bands. Like there is allocation things for that, and the FCC will try and find you and fine you. So there's more like bureaucratic restrictions to that, but physically there's no restrictions to limiting something to a certain frequency. Can you explain the concept of gain? I believe gain, and I don't have the direct definition for this, but the gain is a definition of how many decibels from, or, well, I guess not necessarily decibels, but how much power and how well that frequency is being received by the radio. I think it is actually measured in decibels. I've looked through and read through like some antenna theory stuff, and I've been starting that book, and most of it's like, oh hey, if you're using a quarter wave antenna, it's only going to get a gain of like 1.9 decibels versus a dipole getting 2.6 decibels. So, yeah. Expected it to be a much higher barrier to entry. Yeah. It used to be. Software-defined radios are super, super cheap compared to hardware now. At least with some of the stuff. Like, FPGAs are still ridiculously expensive as a technology, but they're getting cheaper, and they are cheaper than buying hardware for one specific thing. So they're becoming very adaptive, and it's super cool to see that. Yeah, and you can always tune the radios to any frequencies that are within the frequency range that they're defined there. So. Sweet. Is there any other questions that you guys have for me? Have I messed with intercepting and attempting to decrypt encrypted traffic? That's not necessarily a... well, okay, that's kind of a legal gray area there. With, like, encrypted trunked radio systems, you could technically listen to them if you somehow find a hardware key, or if you somehow find a key for the encryption. Getting the key for the encryption is going to be the hard part. But, like, for example, news stations will often get the encryption key as well, because if they don't have the encryption key to encrypted radio systems, they can't listen. And there was a whole ordeal where when police were moving to encrypted radio systems, news channels were trying to sue the city and the police stations for not allowing those to be public for apparently public safety. So that's technically a gray area. If you can if you can somehow calculate or get an encryption key to listen to encrypted traffic, technically you could do that, but good luck. So yeah. Airwaves are public property, but it is technically a gray area because legally encrypted traffic something CFAA. I don't know if it's actually under the CFAA, but if it's like military traffic and you decrypt it, you're gonna have problems regardless of whether it's legally on the books or not. Like, they're going to give you a tough time. So yeah.
If I may ask a question,
Sure.
between like the Blade RF and the Hack RF, are either of them a bit more suitable for playing with like low power applications like QRP transmissions?
Um,
So speaking more specifically of like receive sensitivity.
yeah. So for receiving, it shouldn't be that big of a deal as long as it reaches the frequencies. The more important thing is going to be your antenna with SDRs. With transmitting, it's going to be a lot different, and it's going to be still dependent mainly on the antennas. I don't know what frequencies QRP is like operating on.
QRP is in like very low power.
Oh, okay. It should handle fine. I don't see any reason why it wouldn't.
Thank you.
Yeah, you're welcome. Oh yeah, for sure. It would be transmitting for on QRP with SDR would be kind of a problem, but as long as you're able to get onto those frequencies, it would be just fine. I don't know. Again, there would be environmental factors there, but you would most likely be okay. So. Yeah. Yeah, antennas are going to be the biggest issue for transmitting. They're not as necessarily important for, like, even with, like, ground components, they're not necessarily super important for receiving. Like, I can receive on my Hack RF1 without a ground component, but it's not as effective as if it has a ground component where it can actually resonate. So. How does the realms of SDR and RFID overlap, if any? Yeah, you can do RFID research with SDR. They are anything that's a radio frequency gets lapped into software defined radios. Near field communications is part of that too. So you could do research with that. It would depend on some factors, but I think you would be able to do most of it. There wouldn't be any hardware issues to my knowledge with RFID or NFC. Yeah, SDRs are really cool. They can do a lot, but it may be more cost effective to just buy something specifically for NFC or RFID if that's something you're specifically interested in, or if you're trying to do things like cloning or some kind of research with like things like Proxmarks. Those may be more effective than trying to buy a whole bunch of SDRs and trying to get that to work. But that said, it is all still operating on, I believe it's like 13 megahertz. I can't remember the RFID megahertz off the top of my head, but 30 kilohertz. That's what it was. Okay. Yeah, I was way off. For some of it. They're operating all over the place, but yeah. Are you aware of any consumer available SDRs that can support multiple bands at the same time? So, are you talking about bands like 2 meter and like 70 centimeter at the same time? Because those are going to be really wide ranges. If we go back in the talk to like some of this stuff, again, it's going to be dependent on your bandwidth. So, trunked radio stations usually will have like, I don't know, a range of 10 megahertz sometimes, or even up to 20 megahertz. So like the Hack RF1 may be what you're looking for. But if you're trying to span from large bandwidths outside of like your Blade RF may be a good choice. There's probably some USRP specific radios that you could do with that you could probably get a couple of different bands at once, but it would be they would be rather expensive in terms of like cost effectiveness. That would be my main thought process. Yeah. But for bandwidth, like if you're trying to get like the widest bandwidth possible, I'm pretty sure that they even have like frequency scanners out there, but they're only just going to look for those frequencies. They're not going to be doing anything like digital signal processing or interpreting stuff. Pen testing for like 5 gigahertz, that's totally easily capable. I mean, like you can do that with the Hack RF1. 5G NR. I don't know how big those bands are, but oh, I see. Like LTE 5G. Okay. Yeah. Yeah, I would have to look into the actual bands. I don't know how big those are. Um, but that would be looking more at like the specification of how wide each of those bands are. So I think 5G in general is like it also depends on like if it's low band or high band waves, but I think it's like 300 megahertz to or like 3 megahertz ranges. I don't know about anything above like 24 gigahertz. Like those high band ones are going to be kind of hard. I don't even know if there's really a ton of software defined radios that would help for that, but yeah, like low band you could check out for sure. Yeah, millimeter wave, like the N260 stuff, that's not gonna I don't know if any software defined radios to my knowledge that would even get up to those frequencies. And then like 3.7 gigahertz would be just fine. You could probably do the low band and the mid bands with Hack RF or Blade RF or B200s. Sweet. Any other questions? Oh, right. I think there was one earlier about talking about the hardware. Yeah, so the hardware's a little bit complex, but essentially what it's doing is instead of there being things like an actual amplifier, mainly in the actual radio components itself, uh, it is now a digital audio converter, um, and it will, so the antenna will take in the radio frequencies, and then it will get converted to a digital signal, um, from that analog signal, and it'll be converted to that, and then it will be passed into the processor and then offloaded onto a computer, or if the hardware itself is has a processor, then it'll pass it through that processor for digital signal processing. So I don't know if he's still, yeah, he's still here. So yeah, that would be a pretty basic overview of that. But it can be like, the hardware can get very complex, depending on the radios, and like even just like hardware radios can be pretty complex too. Things like simple like ham radios are really cool to look at from an electrical design, but like the Kraken SDR there, that is very complex, because even though it's 8 of these RTL SDRs in tandem, they have a couple of real-time clock components that all work together to keep it all in sync. And then that's all, patched up, and then they have the antennas to direction hunt. So if you're interested in more about like software-defined radio components and stuff, like the HackRF1 is completely open source. I had to actually fix mine and resolder some of the pads, and I probably wouldn't have been able to do that or have knowledge of what diode was being used without it being open source. So if you're ever curious and wanted to look through all of their 3D models and like CAD models and diagrams, there's a bunch of stuff. Yeah, if you want to throw YouTube videos in here, go for it. I don't mind at all. Sweet. Well, I'm going to stop recording, but we can continue.